Hello, welcome to the last video for this week. We're going to do another string related algorithm, and maybe it's a bit of a stretch calling this string related, but I want to talk about data compression actually, in particular for text file compression. And you can apply this technique for general binary data, but it just makes so much more sense when you see it's done on alphabetical characters. So that's what we use. The motivation is that when you have a character and you're storing that on a computer, each character will take 1 byte because that's the ASCII value. Can we do better? Yes, we can, and we actually do. By the way, there's a great video here by the number file. I think it's called the number file. I'm not sure. Tom Scott. This guy here. So do give it a go. Check out that video because it's a really great explanation and it's done on a much better production budget than mine. So it'll be much better than mine. That's okay. I'll accept that. Can we do better than that? Yes, we can, and yes, we do. And by the way, there's a great explanation here on the YouTube channel. I forgot the name of the channel, but it's this guy here, Tom Scott. So it's a much better video than mine. I can accept that. He has a much higher production budget than mine. So do give it a look for a short 6-minute video on this topic. It's really great watch. Now let's go back to what we're doing. So yeah, I claim that we can do better than just 1 byte per character in our computers. And I use an example here. I should test this. You can try it yourself. I wrote a bunch of I wrote a bunch of sentences here. The quick brown fox, yada yada yada. Same line copied over and over again. I don't know how many characters there are, but it says here I need 3,000 bytes for it. I'm not sure if there's actually 3,000 characters, maybe, but this file here, 3,000 bytes. Okay. And then I create another file. This is just the lorem ipsum. It's a much shorter file, and it says 1,000 bytes. It's about 1/3 maybe. It's about 1/2. I'm not too sure. Anyway, so all that seems fine. You have a 3,000 bytes 3,000 byte file and a 1,000 byte file. That's all right. And then I zip it. I zip both files. Now, what I found is that with the first file, the longer one, when I zipped it up, it was only 262 bytes. So it went from 3,000 bytes into 262 bytes. While the second one is still 665 bytes. Went from 1,000 bytes to just 665. So what's going on here? Now, this is only for the zip file when it's compressed. So if you have a normal text file like before, there's no compression here. You just have 1 byte per character. But when you compress it, you can do some savings. Right, again, 1 character normally just 1 byte. But 1 byte is 256 different characters. Like there are 256 different values. And in English, at least, we don't have that many characters. Even if you take into account capitalization, you have 52 letters still. You take numbers, that's another 10. You got other symbols. I don't know how many symbols you have. And even with the symbols, when you write the text file, how many times are you going to see those funky symbols like tilde or less than or greater than? So the idea is, what if we use a variable length code instead? Don't use ASCII. Use a variable length code. What do I mean by variable length code? All right, let's say that instead of 8 bits, you use only 7 bits per character. And we can do that. With 7 bits is still 128 characters. That's still quite a lot. Okay. But can we do better? All right, let's say you want to compress this anonymous quote here. I'm not going to try to say the second part of that sentence. All right, the assignment is due next week. and there's a lot of E's. We really don't have that many characters here. We don't have X, we don't have Z, we don't have Y. So why don't we just use a shorter representation? Like maybe there's only like, I can't count, but you only have alphabetical characters, so you're gonna have less than 64. You can use 6 bits, right? But what's even better, we can use just 1 bit to represent E, for example. Right, so every time you see 1, that's an E. Well, okay, actually that can't happen. We have to be careful, because if you use 1, like the bit 1 to represent E, and let's say you use the bit S, the bit 1 to represent S, then you can't differentiate between the two, because when you see like 1111, is that E or SS, right? So that's what I mean by variable length code. Like you don't have to use a code which is 7 bits long or 6 bits long or whatever. You can use a shorter code for some letters and a longer one for some other letters. That doesn't happen so often, which means that when you represent the text, you're going to make some savings, because the letter that occurs a lot will have a shorter representation. Now, to do this, we use something called prefix codes. So what are prefix codes? It's a coding system where none of the code work is a prefix for another code word. So we can't use 1 to represent E, because if we do that, then we can't have 10, 11, 100, and all the other ones. This will really limit our options, right? Because all those things start with a 1. So here's an example of a prefix-free code. Sorry, I should say prefix code. So as you can see here, none of the code, so that's the 01, 001, 001, so on, none of the code is the beginning of another code, which means there will be no ambiguity, right? When you see a 001, then you're guaranteed there's nothing. 001's got to be an I, because there's no 0011 or 00111 or 00111. There's no such code. So when you read 0, 0, and 1, you know you're done. You know that the next bit is part of another letter. But still, as you can see, the length of each code word is variable. So what we can use is we can use a shorter representation for characters that occur many times, such as the E here. Well, I can't use 1 to represent E, but I can use 1 to represent E. I haven't represented every single character in this sentence here, but you get the idea. If I use 1 to represent E, that's gonna be pretty short compared to using something longer for E, obviously. And the nice thing about previous codes is that if you use a binary tree, you can actually represent these prefix code very nicely. So this is the code that we have. So the way to read this tree is, if you go left, that's a 0. If you go right, that's a 1. So you see how A is 0, 1, and then S is 1, 0, because you go to right and then you go left. Right? So if you have a string of bits and you want to change that into characters, then you can just use the tree. And you can see how the fact that we have all the letters in the leaves, that means that every single code we have here can't be the start of another code word, because if it is, then you won't stop at a leaf. Okay, so at this point, just to make sure that you're still following, number 1, we want to have a variable length code to represent characters. Number 2, these code have to be prefix free, or just prefix code. I like calling it prefix free. And number 3, if you have a binary tree, then you can use that to represent your code easily. Well, you can use it to decode the string of bits easily. By the way, if you want to encode, then you will just store a mapping from the characters to the code somewhere and use that. Okay. All right. So we know this is what we want. we want to have this kind of curve with the nice looking tree. How do we make one? And this was invented in 1952, and this is actually a greedy algorithm. And Huffman proved that this is a optimal prefix code. As in, you can't, the method we're going to go through, invented by Huffman, he proved that you can't do better than this greedy algorithm. And the algorithm is actually very simple. Okay, what you do is you count the frequency of every single character in the document, and then you make a single node tree, or just a leaf, for every character, and the weight of that node, or the weight of that tree if you like, it's a single node tree, the weight of that tree is the frequency, like the number of times it occurs in the document. Right, now put everything inside priority queue and extract the least weight every time. So what you do is you pop two trees from the priority queue, join them together, and the weight of this new tree is the sum of the weights of the two previous trees that you joined together. So if you have a tree weighting 3 and a tree weighting 4, then the new weight will be 7. So when you join them together, it means you make a new root with no value in it, with the two trees as the left and right children. Right, and then you put it back inside the queue, and you keep on doing this until you only have one tree in the priority queue, and you're done. So you'll have to do this n times if there are n characters. Well, sorry, if there are n distinct characters in the document, you only have to do it n times. So I'm going to explain this a bit more. We're going to go through an example. But really, it's a simple algorithm. It's a really simple algorithm. It's not so simple trying to write it, because you need to muck around with the data structure. But just illustrating how the algorithm works, it's quite simple. So let's have this example with how many letters we have here? 1, 2, 3, 4. These 9 letters. So you have the document with 9 letters, and these are the frequencies: 4, 2, 9, 1, 2, 1, 2, 6, 1. Okay. So I'm gonna make 9 trees, 9 single node trees, and the weight of each tree is just the frequency. We can sort it. Well, put inside priority queue, same thing, I guess. I'm just gonna sort it here. And then what I do, I grab 2 of the small trees in there. Then I join them together. This is how I join them, right? Then I put it back in the queue, or in the set, whatever, right? And I keep on doing that. It doesn't really matter which one you pick. So you see that I picked the 2 leftmost ones, but I can also pick the other 2s. So for the next one here, if I have to pick 2 of the smallest weights, I have to pick 2 nodes, like 2 trees costing 2 each. So I can either pick HC or CM, doesn't really matter. I'm gonna pick HC here, make it into 4, put it together. Now I've got to pick the one that weighs 3 and the one that weighs 2, join them together, and that's all I'm doing. Pick the 2 4s, pick the 5 and the 6, pick the 9 and the 8, and then finally you got 1 tree left. Done. And I don't really care about the weight right now. So that is your decoding tree. Or I guess you can also get the encoding from this tree. So if you want to get F, then you have to go left, 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 left. So that's actually 0, 0, 0, 0, 0. If you want to get A, that's 1, 1, 1. If you want to get E, that's just 1, 0. And S is 0, 1. And that's a good thing, because the representation for E and for S are quite short. It's just 2 bits each. Whereas for something like W, which only occurs 1, or F, which only occurs 1, you have 5 bits. So this is the Huffman algorithm. Again, it's very simple. It's just a greedy algorithm, because you keep on picking 2 of the smallest ones, the smallest trees, and it works. And it's proven to be optimal. And we're going to go through that. We're going to go through the reasoning on why this tree is optimal. All right. Now, to show that something optimal, we gotta know well, what does it mean to be optimal in this case? How do we measure it? Well, what are we using this tree for? We're using it because we want to compress our text file, right? We want to create codes such that we can shrink the size of our text file. So, what is the cost of if you have a tree, like, do we know how big the text file is? We actually do. Because we know the frequency of every character. So here, we know the frequency of each character is up here. And for each character, we know the length of the bits we use to present it. So if you just multiply, for every single node here, you multiply the frequency and the length of the bit to represent that character, you worked out the number of bits you need to represent your text. As simple as that, right? You just multiply the frequency of each character with the height of the node, because the height of the node corresponds to the length of the bit representation. So that's what we mean by optimal. If the tree is optimal, if the representation it gives you is the least possible there is, like, as in you can't do better in terms of number of bits, you can't do any better. So how can we prove that? How can we show that? Now, this is a greedy algorithm, and the way we prove the correctness of a greedy algorithm is almost always by using the proof by contradiction. And I call this the standard defense, as in I have to defend my algorithm. So it's like I present my answer, and then you come along and say, nope, that's not the optimal answer. And I go, okay, fine. I have to defend my approach then. So I argue that mine is at least as good as yours. I.e., we both have the same optimal answer. It may not be exactly the same answer, but they have the same optimality, like they produce the same value. And generally that's as far as I go. I just say, look, there's no way you can have something better than mine. I don't have to say that mine is better than yours. I just have to say that, well, you can't find something better than mine. So mine has got to be at least as good as yours, and mine is also optimal. So again, that's the approach that we're going to take. And let's start by looking at what we're doing in this algorithm. We always take the characters with the lowest frequency first from the queue, or from the set of all nodes. We always take the two nodes which have the lowest frequencies. And when we take them, we join them together, so they will be siblings. So let's say X and Y are the two characters with the lowest frequency. So we start this algorithm, we pick X and Y, we join them together. And in the set now, they will be the only nodes that have height 1, right? You have like, they'll be joined together as siblings. And you have one root, an empty node with left child X and right child Y. Anyway, my tree has X and Y at the bottom, and let's say you claim to have a better answer, then yours will not have X and Y at the bottom, or maybe you just have Y at the bottom or something. It will be different to mine, right? Even if you do have X and Y at the bottom, then our tree's got to be different somewhere, and I can apply the same argument. You'll see. I think you'll be able to see that easily once you understand my argument. But for now, let's just say that I do have X at the bottom, and let's say your tree is slightly different and you have A at the bottom instead. So we're just going to swap A and X basically. Now, if A and X, they have the same frequencies, then our answers are the same. They're both optimal. Because it really doesn't matter if it takes 2 bits or 3 bits to present X. Well, you're going to multiply by the same value anyway. That doesn't make any difference. So for our argument, let's just say that A occurs more often than X. Like we just say it happens one more time than X. And also we just say that A is only one level above X in my tree. Okay, so again, this is your tree. This is the supposedly optimal one, and this is my tree. Okay, I'm going to introduce some notations here. We're going to say that fx and fa are the frequency of x and a, and hx and ha to be the height of x and a. If we swap x and a, this means that we're going to need less bits to represent x because it goes up by one level, right? So it goes up by one level up, so you need 2 bits instead of 3 bits. But you will now need more bits to represent a because you put it at the bottom. Now you need to check the mathematics yourself, but the cost of representing x, before we do the swap, so in my tree here, if you want to represent x, then you will need to do hx times fx. And to represent a, you need ha times fa, but we said that the height of a is just 1 less than the height of x. And the frequency of x is just 1 more than the frequency of a. I'm sorry, the other way around. The frequency of a is just 1 more than the frequency of x. So this is the cost of the representation for x and a before you do the swap. Or in other words, in my tree. And in your tree, after the swap, these are the costs. So hx here refers to the original height of x, like the height of x in my tree. Because what happened here is that you reduce the height of x by 1, and you increase the height of a by 1. So the height of a is now the height of x in my tree, right? The frequency is just fx and fx plus 1. That's fine. So make sure you double check the mathematics. If you want to, you can put in numbers on the tree and you try to check it out, see how it works. But this is the cost in my tree, and this is the cost in your tree. So just do the bottom minus the top one. The difference is 1. So this whole thing here minus that whole thing, well, they actually match exactly, right? So they cancel out. So you got minus 1. The difference is 1. So it's your tree costs 1 more. Like the representation costs 1 more bit than mine. Now you can generalize this. If instead of like 1, you have m here, and again, and the difference in height is more than just 1, so you have n there instead. Put inside the formula again. You're going to have nm as the difference between your tree and my tree. So 1 is already the smallest you can have before, like the fact that we chose 1 here, that's the least difference you can have. So no, it's not possible for the alternative tree to be optimal. So in fact, ours is always better. So you can't just swap any node with my bottom one. You won't have a better answer. So that's pretty much the argument for why the greedy choice is correct. Now you might want to play around with this, confuse yourself. Like I said before, like put some numbers there. Put the frequency on A, B, X, and Y, and then see the numbers for yourself. Work out the how many bits you need to represent the text, and you will see that the one on the left, the one with the lowest frequency characters is at the bottom. The one on the left will always be better. Okay, so that is the proof, if you like, for the optimality of the Huffman tree. You can find this proof in the textbook, I think in chapter 16 on the greedy algorithm. It's a bit more thirst there, it's a bit more it's very detailed, but as long as you understand the logic here, that should be fine. Again, like in this unit, I don't expect you to be very mathematical. Just give me the logic. And here, hopefully you can see how it works. Alright, you can also show optimal substructure with the usual cut and paste algorithm. Sorry, I shouldn't say algorithm, the cut and paste technique. And we can discuss that in the workshop. I don't think a lecture is a good place to go through that. Also, a good practice if you try to write an implementation. Like I said, it's actually not easy to do this because you have to worry about the data structure. You have to use a priority queue, and you have to write a class maybe to represent the nodes, because like a tree must have a value. So yeah, it's good practice if you can go for it. All right, I think that should be enough for Huffman Coding. Hopefully you find that interesting, and we're going to be talking about graphs later after this. All right, thank you.